So this week when we looked at integration, we also looked at using integration to be able to solve differential equations. So in science, a huge number of things are given to us in the form of a differential equation, such as in chemistry, we can look at the rate of a reaction, the rate of which a substance is consumed in a reaction, and how the concentration of it changes with time. Or I can look at it using phase behaviour. This is the Clapeyron equation, which relates the enthalpy of vaporization, the enthalpy of boiling, to the pressure and the temperature. Or I can look at how partial differentials change. So in this case, I've got a relationship for the total Gibbs energy of a system, and clearly this has more than one variable in it. And so I can integrate these even though they're partial differentials as well. It's the same rules as normal. Or if I want something that's much more basic, acceleration is the rate of change of velocity, how the velocity changes with time. So you've been solving these, whether you know it or not, for a number of years. But we now need to look more formally at how we go from this differential form of the equation to something that we can use, because it's very difficult to know what this value dA by dt is. So I'm just going to take this case of the rate of reaction. dA by dt is equal to Ka. And I'm going to try and turn this, or I am going to turn this, from the differential form to the integral form. But what I'm going to do is I'm just going to switch it up slightly to make it look slightly more generic. Here I've just replaced everywhere A was, I've replaced it with a Y. Everywhere X was, or everywhere T was, I've now replaced it with an X. So my equation has become this, dy by dx is equal to minus ky. Now what I need to do is I need to make it so that all of the y's are on one side and all of the x's are on the other. And what I want to do is I want the dy to be on the top. So I want all of my y's on the left-hand side of this equation. I want all of my x's on the right-hand side of this equation. So here I am just rearranging this slightly to end up with my y's on one side and my x's on the other. And so dy by y is equal to minus k dx, or 1 over y dy is equal to minus k dx. So now this is arranged into a form that I can integrate it. So I can just say that I'm going to integrate it here. 1 over y dy is the integral of 1 over y dy is equal to the integral of minus k dx. And if you've written it in a slightly different form, this is exactly the same thing. So normally when we integrate something, we have a constant of integration. But when we have a definite integral, we don't need that constant. The reason being is because we're integrating between two very distinct values. So here, what we need to do is we need to set up our limits of our integration. And so I've said when the x is equal to 0, it's basically the very start of my reaction in this case, I'm going to say that I start out with an amount a0. And when x is equal to a new value, I've called it t, relating it back to the time that we started off with, I'm going to say let our y value be a at time t, whatever that is. I just need to put this number in. So I take my integral and I apply these limits to it. Now, what I always do, it's easier to see it on the time side here, but I put my smallest value on the bottom and my biggest value on the top. If I get them the wrong way around, I'm just going to end up with lots of negative signs coming in, and they'll all cancel out, so you'll still get the same answer. So it doesn't matter if you get them the wrong way up. Just make sure you get the right pairs together. That's the important thing. So here, I've got my integral, I've got my limits, I'm going to integrate it, and I'm just going to look at each side separately. So I'm going to start with the left-hand side, the side with y's on it. So my integral between a0 and at of y to the minus 1, or 1 over y dy, is equal to the log of y. And I need to have the log of y between these two values, at and a0. So what I do with this now, I've got my integral, I'm going to substitute that at into the value of y, and then I'm going to take away a0 when it's substituted into this. So this is just the log of at minus the log of a0. I'm done with my left-hand side just for the time being. Now I'm going to look at my right-hand side of this. And so this side is minus the integral between 0 and t of k dx. I integrate A constant, that's basically a constant times x to the 0. Anything to the 0 is 1, so I can almost imagine this as x to the 0. And so I add 1 to the power divided by the new power. So this becomes minus kx when I integrate it. And I need to have that between the values of 0 and t. Now I substitute t back into minus kx, and I end up with minus kt. And then I'm going to take away when I've substituted 0 in. So I end up with minus, and then minus k times 0. Anything times 0 is equal to 0, and so I end up with just minus kt on my right hand side. So combining these together, I end up with the log of at minus the log of a0 is equal to minus kt. So I'm going to rearrange this now. The reason I'm rearranging it is because I want it to look like y equals mx plus c. So I've rearranged it here. I've clearly got my gradient and my x value because they're multiplied together. And so that's clearly my k and my t. And so I want to have my a0 on that same side of the equation. And so now this looks like y is equal to, in this case, c minus mx. The value of y is the log of a. The value of x is equal to time. The gradient m is equal to minus k. And the intercept is equal to the log of a0. And so I can plot that nice and simply with the log of a on one axis, time on the other. Sorry, it's dropped off, but it's time on the axis. And the gradient is equal to minus k. So I'm going to just present an alternative method here without using limits. So I'm just going to start off in this case again with this differential rate equation, a kinetics rate equation. So here I'm just going to integrate this straight off. So the integral of 1 over a, I've separated my variables just as I have before, I've not gone into it, into the separating of it. It's just the same as it was before, and so I'm integrating just basically the same things. But because I'm integrating this without limits, I need to have a constant coming into this. So I integrate 1 over a, and that becomes the log of a. I integrate minus k, that becomes kt. But I need to have plus c. So this is equal to the log of a is equal to minus kt plus c. So how do I know what my value of c is? Well, I'm just going to say let t equals 0. Yeah? So I'm going to say then when t is equal to 0, clearly I have something left over, because when t is equal to 0, the minus kt term disappears. And so my constant c is equal to the log of a0, because that's what's going to be left over. So I can then rearrange, I can then substitute this back in for my value of c, and so the log of a is equal to minus kt plus the log of a0. And again, this fits the form of y is equal to mx plus c. So my general approach for solving differential equations: I need to arrange my like terms together. I want to make sure that my dy or my dx or whatever it is always on the top. And so I know which side I need to bring my terms to. I then integrate each side and apply the limits and rearrange it to be in the form of y equals mx plus c. I hope this video was helpful. Let me know if you need any more help.